Hey y'all, welcome back to the channel. My name is Jeffrey. Today I'm going to go over some Hardy-Weinberg equations and some example problems with autosomal recessive, X-linked recessive, and autosomal dominant disorders. Okay, so let's dive right into autosomal recessive. The Hardy-Weinberg equation is going to be the same for everything. It's going to be p squared plus 2pq plus q squared is equal to 1. Now, in this case, we are assuming that Q is going to equal our allele frequency for our recessive disorder, okay? So this is going to be the diseased allele, okay? So now that we have that out of the way, the incidence of this diseased allele being observed in the environment is going to be Q squared. And that makes sense because those who are heterozygous are not going to typically express this diseased allele. So for cystic fibrosis, for example, you need both alleles to be diseased in order to see a patient with cystic fibrosis. Now, the allele frequency is how much of that actual allele is out there in the environment. So in this case, we would have to count all of the alleles for that disease. In this case, if we're talking about cystic fibrosis, we have to count in also those individuals that are heterozygous, right? So in this equation, we're assuming that p squared is going to equal our homozygous normal, 2pq is going to be our heterozygous, and q squared is going to be our homozygous recessive, right? So to calculate allele frequency, we would need to have all of the q values together. In this case, it'll just be the square root of that q squared value. And if we're trying to find out the frequency of our heterozygotes, how many heterozygotes are out there in the environment, we would just do 2 times that allele frequency, okay? For our X-linked recessive disorders, you're going to use the exact same equation. Now, for the incidence of males, you have to keep in mind that males are hemizygous, right? They have one X and one Y. So either they are going to be affected with that recessive disorder or they are not going to be affected. So that 2pq value is not going to apply for the males, right? So the incidence for the males to be affected is just going to be that q squared value. You're not going to take into account that 2pq at all. And now, if we're going to take a look at the proportion of female carriers, that's going to be 2pq, right? And the reasoning for that is because um, they are the only ones that can possibly be heterozygous, right? They are the only ones that can possibly have both that dominant allele and that recessive allele, okay? Now for autosomal dominant, you're going to use the exact same equation here, and the incidence is going to be 2pq. In this case, the reasoning why I say that this is very rare for homozygous dominant is that for those dominant disorders, for people with dominant disorders, if they are homozygous dominant, they typically do not survive. They are either not born or they don't live long enough to reproduce. Okay, so it's going to be very rare for a homozygous dominant. So in this case, we can just take off that q squared value if we're assuming that the dominant is going to be the q, right? So we're only looking at heterozygotes because heterozygotes are going to manifest with the disorder. And since q is essentially 0 or close to 0, we can think of this equation as 2p, okay? And then the allele frequency is just going to be p, all right? So if we move into some questions here, and I'm asking, so the population frequency for all 3 of these diseases that we're going to talk about is 1 out of 250,000, okay? So the question is find the allele frequency for each of these disorders. Now, if we look back to autosomal dominant disorders, we remember that the incidence is going to be 2pq, right? There's no homozygous dominant. So you're going to have 2pq is going to equal 1 over 25, 250,000, okay? In order to find that p-value, you're actually going to have to divide by 2 because remember, we're looking at the population frequency. That's going to actually equal to our incidence, right? So as a result, you're going to have to divide by 2. So the allele frequency in this case for this autosomal dominant disordered achondroplasia is actually going to be 1 out of 50, 500,000, sorry, right? Because if you move the 2 over, it's going to be 500,000. For autosomal recessive, or in this case, hemochromatosis, you have to keep into account that p squared is going to equal your incidence value, so 1 over 250,000. And to calculate that p-value, you're going to square root it, and as a result, you're going to get 1 over 500, right? The value gets smaller because as you square root a fraction, you're actually going to get a larger fraction, okay? So 1 over 500, and that's not all because remember, we have to take into account that 2 PQ, right? So when you divide by 2, it's going to be, sorry. So P is equal to 500, but you have to remember that you have to double this value. And the reason why you double it is because you also have to find the allele frequency for those heterozygotes, right? So you have to multiply by 2 to get to that 2PQ value. So then that 2PQ value is going to equal 1 over 250, okay? And then for your X-linked recessive, you have to keep in mind that you do not have that homozygous dominant either. So for X-linked recessive for males, it's just going to be the exact same value. It's going to be 1 over 250,000, right? Because of that entire equation, you only have that p squared plus 2pq value, right? And this is just going to equal to your p-value. And then for your for the incidence of the allele frequency for the females is just going to be you have to multiply it by 2 because that's your p-value, and you have to multiply by 2 for the females. So it's just going to equal to 1 over 125,000. Okay? I hope that made a little bit of sense to you guys. I hope that you found this video helpful, and have a great day.